Petar, the floor is yours.
Thank you for the introduction. Is the mic okay? All right, great. So these days we heard a lot about obfuscation of Android, and I'm going to talk about the inverse process of how do we remove obfuscation, or how do we deobfuscate applications. And so I will present you a system called dguard that was developed by Benjamin Bixel, Veselin Raichev, myself, and Martin Vechev. We're all from the Software Reliability Lab at ETH Zurich. So before I begin, so why do we care about deobfuscating applications? Although we talked about this already in some sense. So as we all know, most of the applications today are distributed on Google Play, and they're distributed in the form of Android binaries or APK files. So in particular, the source code of these applications is not part of this binary. So this means that if you want to inspect the application, how it works, how it handles, for example, confidential data, personal data, this become much more difficult because you only have the binary. Not all the applications are like this. You also have repositories like F-Droid, where all the applications that are distributed are open source. So for those, we do have the code, and we can inspect and see how they work. However, the vast majority of the applications today are distributed in binary format. So in Google Play, we have something like 2.6 million applications. In open source repositories, we have several thousand, so it's much smaller number. All right, so for these 2.6 million applications, interesting questions are, well, which ones are malicious? We would like to know which ones include vulnerable third-party libraries. These are all interesting questions. Unfortunately, they're difficult to answer without having nice readable source code of the application. So why don't we have nice readable source codes? Let me give you a simple example. On the left, you see the source code of a code snippet of an application where, so we have an application code, it implements a class DB helper, has some method, execute SQL. And so in particular, all the program elements like classes, fields, methods, they have nice descriptive names. And not all the names are application specific. Some of those come from the Android API. Like there's the SQLite helper class, which is defined in the Android API. And simply by looking at this piece of code, it's fairly easy to understand what this is doing. So this is implementing some kind of database functionality. However, before we package this application into a binary, what happens is this source code would go through something called layout obfuscation. So this is performed typically by ProGuard, which is the most common kind of obfuscation that we have in Android nowadays. And as a result of this obfuscation, all the application-specific program elements, their names are replaced with short, meaningless identifiers. For example, the class name is gone, the field, the package name is ABC. So that's what we get after obfuscation. And importantly, not all the names would be obfuscated. So those that are part of the Android API would remain, because these are not defined by the developer, and the obfuscation mechanism should not touch those. And I think the contrast is clear. So if I look at the code on the right, it's much more difficult to say what this application does. This poses a number of different security challenges. So it becomes more difficult to inspect how the application works. Importantly, also, when this process of obfuscation is done, the way third-party library is obfuscated is the same way as application-specific code is obfuscated. So this means it becomes impossible to distinguish any third-party code that was obfuscated as part of the binary. So we don't know if the application had any vulnerable libraries that were used to build the binary. And many other security problems, like we would like, it becomes difficult to check if code duplication, code stealing, and so forth. So the central question that we ask in this work is, well, can we reverse this process? Can we go essentially from the obfuscated source code and produce the code that the developer originally wrote? And intuitively, if you think about this, it becomes like, intuitively, it's a very difficult task, right? Because once the names are removed from the source code, how are we going to go about finding out what they were at the first place? Well, however, we show that this is possible. And to show this, we built a system called dguard. This system is publicly available, and you can check it out. It's apkdguard.com. And this system can quite accurately reverse this process. So with 80% accuracy, the obfuscated program elements are renamed back to the original names that were in the source code. That's pretty high accuracy for doing this kind of deobfuscation. And to give you some better idea of how the system works, I will give you a short demo. So this, once you go to the website, that would be the web interface of our system. And what you have to do is you have to upload an APK file to it in order to deobfuscate it. So then once you click upload, this gets uploaded into DGuard. And then what it would do is it would first deobfuscate all the meaningless short names, and then it would decompile this to show you the result into Java. And if I scroll down a little bit more, you would see that it would also let you download, for example, the source code. If you want to download it and grab it to check something on it, it would also allow you to download the deobfuscated APK, which you can download and run and start debugging or reverse engineering. And also it would try to predict all the third-party libraries that were imported in the application. So it would give you a list of all the libraries that have been discovered. And to give you an idea of what's the before-after effect when this deobfuscation is performed, so here I show you for the class that you saw on the back, because you saw only the deobfuscation. So this is on the left, you see the same application that I just deobfuscated. On the left, you have the obfuscated version, and on the right, the version after it is processed by DGuard. And I think the result is quite clear. On the left, we see that all the class name is missing. We have just AF. All the fields are missing, and it's quite difficult to see what this source code implements. And on the right, this is all replaced with quite meaningless names, making reverse engineering much more easier task. Okay, so going back to my slides, that was a demo. So we released this system in October last year, and it quickly became popular among the Android community. Many people started uploading their Android binaries to it. So far we have over 100 gigabytes of Android binaries uploaded to our system. There were various Reddits and posts and tweets about the system. People are wondering how is this possible to go, to figure out what were the names in the first place. One guy on Reddit even asked, like, what's the point of having ProGuard if there are systems like this? And another Redditor responded that he made the effort to ask the ProGuard creator of how difficult it is to deobfuscate ProGuard obfuscated applications, and the creator apparently said that this is essentially impossible. So there's a mismatch here, because we show that it is actually possible, and we can do this with quite high accuracy. All right, so how do we do this? I think there are two main components that I will explain. So you need to have large amounts of open source code, and this we have. We have repositories like Bitbucket, GitHub, and so forth, and machine learning. These are the two ingredients. So this is how DGuard manages to do this. So first, we start with a large number of open source, unobfuscated Android applications. And as a first step, we have a learning phase. And intuitively, in this phase, we want to learn how programmers or how names are assigned to program elements. And to achieve this, so first we run some static analysis on the application, on these applications. And intuitively, the idea here is we want to derive some semantic representation of this application. So we want to derive what are the program elements in the application, how are they related with one each other, and so forth. Having derived this semantic representation, then we have a training. And the idea of this training phase is to learn a probabilistic model that captures how names are assigned to program elements. And once we have learned this model from all these thousands of open source applications, we can use this to deobfuscate applications. So this is done during this prediction phase. So the learning phase is done once and for all applications. So we do this once to compute this probabilistic model, and then we store essentially this probabilistic model in DGuard. And then we run the prediction phase for each individual application. And the way this works is, so we start with the obfuscated code, We run the same kind of static analysis to derive what are the program elements and their relationships. Then we can use the probabilistic model to predict, to run map inference to predict what are the most likely names that should be assigned to the obfuscated program elements. And once we have predicted those names, we can simply transform the application by plugging in the names that we predicted. That's the idea. So there's several parts here that are critical to get right in order to get this to work. So it is important to pick the right semantic representation. So it's important to pick something that is compatible with whatever probabilistic model you're going to train. And also it is important to abstract away some details to do the static analysis, because if you want to train this model directly on source code, that's not going to work. So for the rest of the talk, I'm going to give you a bit more detail on how these steps are performed. And I'm going to start with the probabilistic model, which is like the merging, the thing that unites these two phases. All right, so here in DigArt, we use a probabilistic graphical model. And these are very well-known probabilistic models that have been used in many other domains, for example, in computer vision, in speech recognition. And here in DigArt, we use them for the task of deobfuscating Android applications. And I'll give you a quick crash course on these probabilistic models and how they work. So as the name suggests, these models, you have a graph over variables. And these variables are partitioned into two kinds. So you have known variables, which are the ones for which you do know the names, and unknown variables, which are the ones for which you want to predict the names, okay? And in the context, in DigArt, we deal with programs, so these graphs represent the programs. So in particular, the nodes represent different program elements, such as class names, methods, constants, types, fields in the code. And here on the right, for example, you see the source code of the application from which we derive the graph that is over there on the left. For example, we would have the node A to represent the class A. We would have another node SQLite helper to represent the class that it extends. So once we have derived these nodes, then they are connected with different kinds of relationships. And these relationships essentially capture, how these program elements relate. For example, A extends the SQLite helper, so we would add an edge to represent this relationship between these two program elements. And so it is important to get these relationships right, and there's more detail on what are the complete, all kind of relationships that we use in DigArt. So if you're interested in exactly how these graphs are derived from the APK, you can find a detailed report on this on the website of the system. All right, so once we have the graph, then each of these edges that connects these program elements is associated with different feature functions. And now these feature functions, they define concrete names that can be assigned to the program elements. For example, we would have the relationship, the edge on the top extends, which is associated with two feature functions, F1 and F2. And according to these feature functions, we can assign the name dbutils or dbhelper to the class name A. And these feature functions, they also have a weight which intuitively gives you the likelihood of how likely is the name that they suggest to use to deobfuscate this program element. So, for example, dbutils is considered more likely because the feature function F1 has a higher weight than the feature function F2. Okay. So the whole point of having this graph and these feature functions is that the graph, together with the feature functions, defines a well-known probabilistic graphical model called conditional random field. And I will not go in much detail there, but the point is that it defines a conditional probability. So it defines the probability of any assignment of names to the obfuscated elements, given the names of the elements that we know. Okay? So technically, the way that's done is you have to evaluate the feature functions, multiply it by the weights, and then this would define what the probability is. So what's the point here? If I have this probabilistic model, I can simply check, I can use it to find the names that are most likely. So that's the goal. And if I start with a new obfuscated application, I can derive the graph for that application. What I don't have initially, at this point, I don't have the feature functions and the weights associated to these feature functions. And these can be learned from large code bases like GitHub and Bitbucket. This is done during this learning phase, which I'm going to explain now. Learning. So in the learning phase, we start with, as I mentioned, a large number of unobfuscated Android applications. And we also, this phase, we have these feature templates that define the structure of the feature functions that we're going to instantiate from the data. And to give you some idea of the scale here, so we start with several thousand unobfuscated applications. And the feature templates, these are manually defined templates. And we have 28 of those in DGuard. And in the first step during this learning phase, we run our static analysis to derive what are the dependency graphs that correspond to these applications, so the program elements and their relationships. And at the same time, we also instantiate all the templates with concrete feature functions. So again, to give you a notion of the scale, so these graphs are small on the slide, but they're big in practice. So another application, the graph that you would derive from it would be something like 1,000, 10,000 number of nodes. And the number of feature functions that we instantiate from the data is in the order of hundreds of thousands of different ones. Okay, so here at the bottom I get the feature functions. What's missing, the last missing component, is the weights that will be associated with these feature functions. And this is done during training, where essentially the goal is to compute weights that maximizes the probability that the obfuscated elements would be correctly predicted. So now that here we can train this, I mean, we can maximize this because these are unobfuscated applications. So we do know what are the correct names given in the source code. So that's what allows us to compute the weights here. All right. And the outputs of this learning phase is the feature functions together with the weights. That's it. All right. Moving forward, so this is a high-level idea of how the learning is performed. Now I'm going to explain to you how the probabilistic model that is outputs from this learning phase is used to deobfuscate applications. And here's how it goes. So we start with the obfuscated source code. We run our static analysis to derive the dependency graph that corresponds to this application. So in this example, this is the same example I showed you before. So we have two program elements that have been obfuscated, so namely the class A and the field B. And now, because we have already learned the feature functions and the weights, we know precisely what feature functions are associated to each of the edges in this graph. Okay? And now these feature functions, they tell me what are concrete names that can be assigned to these program elements. For example, the class A can be called dbutils or dbhelper. Then if I look at the field B, this one can be called either db or instance. And so you get a total of 4 possible combinations in this example of how we can deobfuscate that application. And if I apply the equation that I showed a few slides ago, we can compute the exact probability score for each possible assignment of names to the program elements. So here we have 4 combinations, and to pick the highest one, we run map inference. Okay? So in practice, of course, we cannot brute force and go over all possible combinations of names because these are very, very large graphs. But using map inference, we can approximate that result. So in this case, it should return the second row because this has the highest probability score of 1.3. And once we have done that prediction using map inference, this gets plugged into the graph. So we know what are the new names, and finally we can transform the application by plugging in these names into the final source code. And that's the output. As output, we get the obfuscated code of the application. All right. So now one important question here is, well, we're changing names here. We're somehow modifying the application. So is the new application that we output semantically equivalent to the one you provide as input? So this is important because once you start reverse engineering and debugging the deobfuscated applications, you want to make sure you're analyzing the same application. And DGuard handles these cases, so it ensures that the output is semantically equivalent to the input by something called semantic preserving deobfuscation constraints. And this is necessary because Android has rich structures, so it has method overloading, it has class hierarchy, so you cannot freely rename fields, methods, and so forth. So it is configured with different kinds of syntactic constraints and semantic constraints. And Once the application is uploaded to the system, it would run some static analysis to derive those syntactic and semantic constraints that would ensure that the result is equivalent to the input, and then it would preserve those while the deobfuscation is done. So a simple example, if we have a class A with these two fields A and B, then so we would derive a constraint that these have to be different, otherwise we don't get a syntactically valid application, and then this constraint would be enforced while the deobfuscation is done. So similarly here we have two methods that have different names, but the class below extends the one above. So we have to make sure after the deobfuscation these also still have distinct names, otherwise we would get a method overload which would change the semantics of the application. So this is all transparently handled by the DGARD system. All right, so this gives you a rough idea of how this DGARD system works. Next, I'm going to talk a little bit about how we implemented this and how well it performs in practice on real applications. So it's for the implementation, for the static analysis part, we use Suit, which is a popular static analysis library for Java and Android. And for the learning and the map inference parts of the system, we use the Nice2Predict framework, which was developed in our lab. So this is a very scalable open source framework for structured prediction. It is open source. You can find it at nice2predict.org. There are many examples, so you can urge you to go and check it out, how it works. In order to train the probabilistic model, we used the 2000 open source application that we collected from the F-Droid repository. And as I mentioned, this is also the URL where you can find our system. Now, in terms of how well does it perform in practice, we focus on, I'm going to answer 3 questions. So the first one is, well, can DGARD reverse ProGuard, where ProGuard is the main tool that does this kind of, the kind of obfuscation that DGARD targets. Then second question is, can DGARD be used to detect, to accurately predict third-party libraries? And finally, we wonder whether DGARD is useful to inspect real malware samples. All right, let me jump with the first question. So to conduct our ProGuard experiment, we did the following. So we took a lot of applications, the source code of these applications, and then we compiled 2 different versions of each application. So first we compile a non-obfuscated version of the APK, so where all the names in this APK are the same as in the original source codes. And then we also compiled it with using ProGuard, where we want to get where all the application-specific program elements would be obfuscated. Then we can run the obfuscated APK through DGARD to deobfuscate it. And the point is that we can use the non-obfuscated APK as an oracle to tell us whether the names that DGARD predicts are identical to the ones that were in the source code. That's what we did. So let me show you what the data is. So first I show you some data on the applications after we have obfuscated them. So here you see several bars, and they show you, so these bars represent percentages across program elements. So we have fields, methods, classes, and packages, and the right bar aggregates over all different kinds of program elements. And so this tells you that after obfuscating the applications, about 30% of the names remain. So these are the API-specific ones that could not be obfuscated. All the other ones, the remaining 87%, are replaced with short, meaningless names. And let's see what happens after we deobfuscate with DGARD. We get the following results. So there are 2 additional bars, segments on these bars. So the green one tells you the percentage of elements that were correctly predicted. So by correctly predicted, I really mean the name is identical to the one that was in the original source code. And the red segment tells you the cases where DGARD predicts some name, but it wasn't exactly the same as the one in the source code. And the bottom line here is that after the obfuscation, 80% of the names are identical to the ones we find in the source codes. And for some, if you look at the breakdown per different program elements, there are some quite big differences. So if you look at fields, after obfuscation, we have only 1.6 of the names for fields remain in the application. After the obfuscation, this goes up to 80.6%. Another interesting fact here is that you see that for highest accuracy of DGARD is actually for predicting package names. And this is actually quite useful because if we know the correct package names, we can directly predict what are the third-party libraries that were used to compile this application. So that's what we did next. Next, we check whether DGARD can predict indeed third-party libraries, and we did the following. So again, we compiled applications that import such third-party libraries, and once ProgArd obfuscates those, so again, these are treated in the same way by ProgArd. So we essentially all the package names for the third-party libraries would be obfuscated, so we cannot recognize them directly. And what we did is we deobfuscated them again with DGARD, and then simply checked which third-party libraries are imported. So this is easy to check because we can simply look at the package names and see if they identify popular third-party libraries. So we measured this across our applications, and we got the following results. So the precision of doing this was 93%. Recall was 91%. And this means that DGARD is, in fact, quite effective at predicting the third-party libraries that are imported in Android applications. All right, so last question was about, well, does this work for real malware samples? And to answer this question, so we took all the malware samples that were collected in the Android Malware Genome Project. So this is a project where joint effort to collect a lot of different malware samples for Android. And now that here we don't have the original source code, so I can't tell you how it was the exact accuracy of DGARD because I don't have it. But I can share some experience because we manually inspected the deobfuscations. And here's one example, common example actually, that was I found in many different malware samples. So you have a class like this, where if I look at it, I don't know what it does. hard to understand. After DGARD, we observe the following. So I see now that this class is actually called base64. I have a method which is called decodes, and if I check at the implementation of this decode method, I indeed see that this is decoding, doing base64 decoding. This is quite common in malware because malware often tries to obfuscate the strings that it works with. So that was one case where DGARD was quite successful to find such string decoders. And this is helpful because if I know what kind of string decoders are used by this malware sample and where are the methods that implement these decoders, then this can significantly save me time to manually try to find those in the malware. Another case where it was quite helpful is to discover classes, methods that handle sensitive data because it would essentially put the proper names for the fields and methods, and I could simply grab the source code for, say, location or address and so forth, and figure out in which classes deal or handle such sensitive data. And of course, it didn't handle all the malware samples perfectly. We saw heavily obfuscated malware where you see things like reflection, code unfolding, control flow obfuscation, where it's these kind of obfuscation mechanisms go beyond what's the scope of what DGARD can handle, and it was not as useful to reverse engineer these examples. Okay, so that's about results. Now, what's next? Currently we're working on a new version of the DGARD system where essentially we want to make the system more precise, more scalable, faster. And also there is a next generation system that is currently being developed. It's called DeepCode. So this is a new spin-off at ETH. So this DeepCode also leverages large code bases and machine learning to help developers write easier, more reliable, secure codes. For example, it can automatically learn that SHA-1 is insecure by looking at GitHub and suggest to developers that they should replace the usage of SHA-1 with SHA-256, which is quite useful. All right, so with this I'm going to conclude. So in summary, I presented you the DGARD system, which is publicly available at this website, and it is the first deobfuscation mechanism for layout obfuscation in Android. The way what made this possible is really using these powerful probabilistic models that allow DGARD to learn from large amounts of code bases to achieve high prediction accuracy in this deobfuscation. And if you're interested in this line of work, like for example, if you're interested in these products or in research projects or internships. You can find more information on poml.ethz.ch. So there are many YouTube videos and presentations on this topic and other systems that achieve that do similar things. And the second link is the link to our lab, where you can find contact details to reach us and talk to us. So with this, I conclude. Thank you very much, and I look forward to your questions.
Thank you very much, Petar. I'm pretty sure that we have a lot of questions and a few minutes for them. So let's start.
Hello. When you go back to the CRF description, which you have, you basically
almost there. Well, here.
Yeah.
Sure.
So what you do, you basically compute the CPD for the program elements that you have. But do you really compute the normalization constant to form the proper CPD? And because otherwise this would or you just estimate it somehow by computing the likelihood for program elements and then using that to predict the program elements that you showed here?
That's a good question. So we don't need to normalize the probability, because when we run map inference, we're not interested in the exact probability for a particular deobfuscation. We care for the most likely one. So even without normalizing, we just care for the one that gives us the highest score. So we don't do the normalization.
Hi there. Yeah, I have two questions actually. Extremely interesting presentation, Matthew. But the first thing is, have you considered any connection with satisfiability problems in this field? Because it seems to be a kind of a customized ontology on which you could apply SAT-based reasoning. That's the first question.
Do you mean SAT-based in terms of like learning how to satisfy formulas, or in terms of?
I mean, if you need to solve the assignment problem of these free symbols, for instance.
I see. So these are not hard constraints, because we don't have hard constraints. I mean, I can have hard syntactic and semantic constraints that have to be satisfied in order to get a semantically equivalent application. But these are more like soft constraints where, I mean, they're both, to the obfuscations, they're both okay, but one is more likely according to the data that's available on GitHub. So that's why we really need this probabilistic approach that would tell us what is the likelihood of a particular deobfuscation. And the hard constraints really come from making sure the application is semantically equivalent.
Yeah, and this is related to the second question. The second question is, it looks like to be working very well, especially because the kind of obfuscation which is performed seems to be essentially lexical, for what I've seen. Have you considered also transformations that are preserving the semantics? I mean, you're building an AST and semantic representation of that. But if the obfuscator was changing the structure of the code, preserving the semantics, but changing the structure,
yes,
would you be as good as?
Yes, so of course, there are many other different kinds of obfuscation. So this is layout obfuscation that only replaces the names. Also, you have many different, like where you would add codes, dead codes, I don't know, change the control flow, duplicate code, and so on. And so we're working on that. These are also things that can be done, but it's work in progress. We can chat about it offline if you want.
Please.
Just two quick questions. The first one, and it seems I may have missed it, but just the renaming, in my opinion, is a pretty weak obfuscation. So if I would want to deobfuscate it, I'm sure the naming would help me figure out what's going on, but per se, I wouldn't really care about that too much. So I mean, like.
Yeah, sure. So I've heard this response.
Just out of curiosity, maybe I missed something.
Yeah. So let me answer this way. So it's true that there are other. I mean, naming of course helps you, right? It's actually one of the most difficult kind of obfuscations to reverse, because ProGuard, what it does is it's a random step of obfuscating the application that is very, very difficult to go back. If you look at control flow obfuscation, string obfuscation mechanisms, these are often easier to actually reverse, because I can just look at how it's done and figure out how to revert it. So in that sense, it's an obfuscation mechanism that's quite difficult to reverse. And as a second point is, I mean, really this is the most common kind of obfuscation done on Android, so that's why we started with this example.
No, that was just, it seems to me to be not very powerful to do, and other things may be better suited. And another thing that I think goes back to the second question, that's more like of a suggestion, but if you would encode all of the information, like the types that you would expect, and if something is a method or a field, the information that you already had in your model, then you could maybe even do without the constraints, because then your replacements would...
Yes, that's we actually do this, yes.
Yeah.
Yes.
Well, I mean, you said you had these rules, but you could even encode it in the model that you find, then you could maybe do without the constraints.
That's very good. That's exactly actually what we do. For some of the constraints where, for example, for equality constraints, we can simply merge those nodes. And we do this because it makes the graph simpler, and then we don't have a constraint to enforce during map inference. So we do that.
Thomas?
Okay, there are maybe 20 or 30 popular Android libraries used in multiple applications in the market. Don't you want to use some kind of syntactic hash or other signature which would allow you to pinpoint a particular library in particular version with 100% accuracy?
So this can be done. People have done this hash-based identification for the problem of third-party libraries. That's what you mean, right? Yeah, so this can be done, and essentially if you look at how these approaches work, so they wouldn't take the hash of the source code, because then the hashes that you would get would not help you identify the third-party library. So they will still go about coming up with features like number of fields, or they will still capture the structure of the code and then hash this. And here we kind of get the same thing, but we get it in a probabilistic, which allows us to be more flexible. So even if the third-party library is slightly modified, for example, concrete example, so when you do POGARD, it would remove some of the dead code. So it would remove some of the methods in the library. So if you simply hash it, you will not be able to identify it. But here, as long as much of the structure of the third-party library remains, we would be able to discover that it is part of the application. So this gives us this flexibility.
Thanks.
I have one last question from there.
Hi, how did you evaluate your results? Because 90% is pretty good. Did you evaluate your test set and training set with the same data?
So you're referring to the third-party library prediction or the name predictions?
The name prediction.
So there we really made sure that the applications are split. So we split strictly training data and benchmark data. So we really did our best to separate those.
And a short second, native?
I'm sorry?
Anything about native code so far, or?
No, this is not handled right now.
Okay, let's thank again Petar once more. Thank you.